I'm just getting my screen back. Okay, well, good morning still. Oh, it's good afternoon already. Very grateful that you've invited us to join in today. It's very interesting for two reasons. On a personal level, I actually lived in Dounreay from 1970 to about 77, so it's really interesting to hear about the history of the programme up there. But much more importantly, I think where we are with the UKAEA today in the Fusion programme, there are lessons to be learnt from the evolution of the fission technology and the fission programme. And of course, a lot of that knowledge now exists outside of the UKAEA. So it's quite important for us to understand how that programme did develop, what went well and what went badly. So Andy started the day talking about the importance of a mission, which is handy because that's how I wanted to start as well. And our mission at the UKAEA is to lead the delivery of sustainable fusion power and maximise scientific and economic benefits. And that's quite nice on the slide, but actually, to be honest, if you walked around the campus at Culham or at our new site in South Yorkshire and stopped someone at random, I'd wager you probably had a 9 out of 10 chance that people would be able to state that back to you. We're a very mission-orientated organisation. And that is quite a nuanced mission. We're not saying we are going to deliver everything ourselves. And we also understand the importance of delivering benefit, particularly economic and industrial benefits along the way. There are 4 goals that sit under this mission, and they're best understood in the context of this arc of development of some of the major international programs. Our first goal is to be a world leader in fusion research and development, and that links strongly with JET and Mars-U reactors, which are both running at Culham at the moment in experimental campaign. We have a goal to drive economic growth and high-tech jobs in the UK, and a lot of that is through supporting UK industry to win work to supply ITER in the south of France. Some very high value contracts being let from ITER. We are looking to enable the delivery of fusion power plants, and we're heavily involved with the EU demo programme and also have our flagship programme STEP. And as a national lab, we also have the goal to create a place that accelerates innovation, develops skills and provides facilities to allow industry to thrive. To achieve these goals, there's 3 environments we really need to affect in parallel. We need strong international partnerships. We need an ambitious domestic programme of our own, and we don't underestimate the importance of having a thriving private sector, and I'll talk about that a little bit more later. We are a national lab. There's 3 cross-cutting overarching capabilities at the bottom in terms of providing facilities and expertise, a place, buildings, infrastructure, and developing people, skills and training. And this slide gives an overview of the international programs. The top 5 bars on here are all experimental facilities. The bottom 4 are actual power plants. And I'll just point out a number of features on this chart. You'll see that JET finishes quite soon. JET will actually finish in 2023. And it isn't a complete coincidence that coincides with first plasma ITER. And just to be aware, you know, ITER is an experimental facility. ITER is not actually a power plant. The 4 power plant programs at the bottom, STEP, I'll talk a little bit more about later. That's our flagship domestic program. We are luckily still involved in and contributing to the European demo program. There is quite a lot of momentum now in the US to develop a pilot plant program. We think it's going to look quite a lot like our UK STEP program. It'll be starting a little bit late, and they're planning on finishing it earlier than we're targeting. And it's important to keep an eye on the Chinese program, because when they want to, they can proceed at a pace and don't always have the same barriers that we have to progress. So fusion needs integrated solutions, and one of the exciting things about UKAEA is that many of the technologies required, we have a depth of experience and significant facilities to support those areas at Culham and now at South Yorkshire as well. We have many years experience running high performance plasmas in JET. We have materials development facilities at MRF, which also do work for fission. Heat is our tritium, or our fusion fuel centre, which has received government investment to develop a 20th scale pilot fuel cycle, modelling the ITER cycle. The mass reactor is focused on diverter exhaust solutions. We have teams learning how to design reactors, both with STEP and demo. I'll talk a little bit more in a minute about some of the test facilities we have for the extreme fusion environment. For remote maintenance, we have our robotics centre called RACE, Remote Applications in Challenging Environments. And we also have quite a large team now supporting our modelling and digital design work with advanced computing infrastructure. And this isn't everything we need for fusion. And an important part of our strategy going forward is deciding what we're not going to do and what we can bring in from elsewhere, either because we don't need to do anything because it can be supported by industry, or because there is a significant strength of capability elsewhere. So you will notice, for example, there's nothing here about specifically about magnet technology, and that's obviously quite a key part of a fusion plant. So just a little bit of an overview of some of our test and qualification facilities, because these are some of the things which might be of most relevance to the AMR SMR programme, and where there might be some overlaps. This is a rendering of a building which is just going up. All the steels are up, but it's going to house the tritium fuel cycle plant, but also the fusion technology group and their applied materials labs. And this is at Culham. And we have a new site in South Yorkshire at the Advanced Manufacturing Park, so in the middle of a fantastic cluster of advanced manufacturing capability. One of the larger facilities which is going to go into South Yorkshire is called Chimera. And Chimera is a test facility that allows us to apply combined loadings to components and assemblies. And by combined in fusion, we're talking about high thermal transients, high heat loads, but also both static and pulsed magnetic fields. So there's no facility quite like this in existence. And the test piece in this graphic is a tritium breeder blanket, which would go into ITER. So we're quite excited to be developing a facility with two partners, Jacobs as a system integrator and Tesla supplying the magnets. And this will provide a facility which will be relevant to the international fusion community. And a big part of this is to validate digital models. So with all our physical testing, we'll be creating digital twins and validating our digital models. One of the problems with fusion is that we can't qualify designs by building subscale prototypes, like in some areas of engineering. So for rapid development, we do need to validate digital models and develop using digital models. Another area where there's some overlap is on thermal hydraulics, and actually we were very pleased to be involved and support BAYES in some of the preliminary work looking at the new national facility. We expect to have 3 thermal hydraulics facilities in South Yorkshire. The largest would be Chimera, and the previous graphic. We have a smaller facility being put together at the moment, which is single phase but very high fidelity in order to verify digital models. And there's a facility we expect to sit between the two in terms of size, allowing us to model some large scale single and multi-phase water flows. And we remain sort of tied into some of the fission strategy on thermal hydraulics testing, and I expect this overlap in programme and sort of support between the programmes to continue. Okay, so our flagship domestic program is called STEP. Our program director for STEP is Paul Methven, and he'd be very keen to talk you through more details on any of this if you wanted to go into more detail. STEP has a very clear mission. They are aiming to deliver a UK prototype fusion energy plant. They're targeting 2040. And as well as delivering a prototype plant, they also need to deliver a path to commercial viability for fusion. So the design aims of this are to achieve net positive energy, which as a plant, an overall plant, has not been demonstrated before. They need to be able to demonstrate tritium breeding, maintainability and availability, and also safety and waste management. Some of the key challenges they need to address are a plasma scenario, the heating solution for the plasma, tritium breeding, materials compatibility and degradation, and then remote handling and component interchange. But it's not just about the technical solution, and there's some areas here where we do need to learn from previous programs in fission. As well as having a technical solution, we need to be able to demonstrate how we can deliver what a lot of people call a mega project. Don't particularly like that term, but I think you all know what I mean using it. We need to understand how to deliver a mega project, and we need to develop the capability in the organization that is capable of that delivery. So it's not just the design we're focusing on. We're also trying to understand how to build that capability, and we're not just building that capability within UKAEA. We need to build it also in the supply chain. We need to pump prime the supply chain and stimulate development in the supply chain. Process we're currently in the middle of is securing and developing a site. There is a site selection process underway. I suspect you have seen some of that in the media. We've had very good response from that call, and we need to understand how we're going to finance this and convince stakeholders to get on board. This just gives a very rough indication of the timescale for STEP. We are working on reference plant designs at the moment, and by 2024 we will be aiming to have a reference concept as we move into the second tranche. By the time we move into tranche 2 in 2024, we also expect to have an operational model which will be fit for purpose to deliver the program. And as I said before, we are targeting 2040 for the prototype reactor. And the last point I wanted to make about the fusion program, and this is my last slide, is that it's not just the large publicly funded programs developing fusion reactors now. There's actually a very large number of small private startups entirely in the private sector developing quite a myriad of different fusion designs, and the amount of venture capital going into these companies is quite significant. And UKAEA, of course, supports that by providing facilities and providing expertise on a consultancy basis, because in order to deliver fusion as part of Net Zero, we have to develop a very vibrant private sector that is capable of developing designs, and the more competition we have in that area, the better for delivery of fusion. Okay, that's all I had for today. I think that's about my 15 minutes.
Thank you very much.
Hand back to you, Simon.
Thank you, Steve, and thank you to all the other speakers in this pre-lunch